But anyway, we'll do some stuff and we'll practice as is the usual. I got you. All right, so when we're talking about domain and range, we are going to express those things in what we call interval notation. Interval notation just looks like this. Like I've got this chart down here. Let's look at the first example. I can get it to scroll, which of course I can't because it hates me. All right. All right. So if you're looking at expressing a domain, for example, right? Because when we're talking about domain and range, we're really separating the XY coordinate grid into a horizontal number line and a vertical number line. And we're addressing each of those components separately. And so to that end, we can express these things either as an inequality or in interval notation. Interval notation will be the most commonly used method that we use. Some conventions for that, right? So that we're expressing this properly. Number one, the smallest number is written first. And when I say smallest, like -5 is smaller or to the left than 5, right? The largest number is written second following a comma. So it's almost like a coordinate pair. Parentheses signify that an endpoint value is not included in the interval, right? We call this open or parentheses. This would mean that the number A, whether it's like 2 or 3 or whatever, would not be included. You've also seen this as an open circle before. And you'll see that flip-flop between those two notations. And then the arrow indicates that it goes on indefinitely, in this case in the positive direction. So we would denote the endpoint of that as infinity. So because we can never get to infinity, and infinity is never something that is included, you will never have a bracket, a closed bracket, these, to indicate any sort of endpoint, including infinity. It will always be an open bracket, parentheses. Right? Okay. So this is just a table. You're welcome to at a later time transcribe it if you want, or you can try to do it now. I'm going to go ahead and just kind of walk through the different stuff. So you have an inequality. X is greater than A. The interval notation just gives me a kind of a list of what is included with that. A and everything above it, not including A. Same thing in a number line, you have the number A, the parentheses or open circle, and then extending indefinitely to the right, which is positive infinity. And then this in words, X is greater than A. So if we were to include A, it'd be X is greater than or equal to A. That would be a closed circle or a hard right. Okay, so just moving down, you'll see this is kind of a reference for you more than something for us to talk about because it is review. So you can see all of the various things. You have a strictly less than, you have a greater than or equal to with that bracket, a less than or equal to, and then getting down to these, this is when we have two boundaries. X is between. Notice this is how we interpret that. X is between A and B, including A, because the bracket is on A, or you have the less than or equal to here. So when you're reading this in inequality notation, like I want to start with the X and read it out. X is greater than or equal to A. X is less than B. And when we combine these, we'll use the word or because it can be either. Okay. Questions so far? Is this by and large or a euphemismus? Yeah, okay. Good. Just making sure. Okay. So let's see here. What do I got next? All right, so I've pasted these little like step-by-step how-tos for me to have there for you to look back on while I'm doing an example. So the first one that we're going to do is given a function in equation form, I want you to find the domain, right? So remember, we did a little bit of this the other day. So what you have to think about is number one, identify the inputs. We've already done this. Number two, identify any restrictions on that input. So one of the examples there is, can you take the square root of a negative number? Can you take the square root of the negative number in a real number situation? No. And so then you'd have to exclude those things that don't work. So you kind of have to use some reasoning here. You kind of have to think about what's happening with particular functions. So let's do an example and apply those steps. All right, so example number one, find the domain
find the domain of the function f of x equals x squared minus 1. And so what you want to think about is, remember, the domain is the set of all possible input values for the function that will give me an output. So for this one, the instructions for this function say take some number, square it, and then reduce it by 1. That's essentially what we are doing. Is everybody seeing how I'm getting that? We take a number, we square it, and we reduce it by 1. Is there any number that we can't do that to? Does it break any rules? No. I can take any number, square it, and reduce it by 1, and nothing crazy happens. Okay. This will make more sense as we start getting to some functions where crazy stuff does happen. And so for this, the input is x, right? So identify the input values. X is the input. There are no restrictions. And therefore, kind of our jumping off point when we're talking about the domain, we start with everything, right? So the starting domain, I'll just put that in quotations. The starting domain is going to be everything from negative infinity to positive infinity. And if there are restrictions, we then start cutting pieces of this out. But this is where you begin, right? So without any restrictions, it defaults to this. That's always the domain of a function unless we have to remove something. Good? But this says that I can take any number, place it inside of this function, and get another number out. Okay? All right. So from there, the domain of this function is simply this in interval notation. And we'll discuss some other notations later, but right now we're just going to work with the interval notation. Let's go again. Example. So this is finding the domain of a function that has a denominator. Okay, so let's say we're going to find the domain. So you're going to have a few basic domain problems. One of them is going to be the ones that don't have any restrictions. This is going to be the second one. Find the domain of the function. And we're going to do a rational function now that has a fraction. So this will be, oh my God, that's so small, x plus 1 divided by 2 minus x. Okay, so step number 1, what is the input? X is the input. And this seems kind of silly to do this now, but when they get a little crazier, it helps. So number 1, x is the input. So when you're working with a rational function that has an x in the denominator, we are looking for what is going to make this not work. So the denominator cannot be 0. Right? Remember, in a rational function, we cannot divide by 0. That's undefined. And so we have to remove those values from the domain because I cannot plug in any number that will make that denominator 0. So the denominator cannot be 0. Therefore, let's figure out where this will be equal to 0. So the question I'm asking is, where is 2 minus x equal to 0? And then we can use the miracles of high school algebra to figure that out, right? So this would be -2, dividing both sides by -1. So at x equals 2, the denominator is equal to 0. The denominator equals 0. This is not allowed, so we remove x equals 2 from the domain. Okay, so how do we do that? What does that look like in the interval notation? Well, if you are struggling to figure that out, I want you to, let's see, let me give you some space. I want you to draw a number line. So if you're thinking, I'm not real sure how to write this, let's draw a number line because the domain is basically the number line for the x-axis. So if this is a 0, this is a 1, this is a 2, this is a 3, -1, -2. Eventually, you might not need to draw a number line. And if you don't need to do it, you don't have to. So the domain of this function, the only thing that I cannot have is this. Right? If you remember, I said earlier that the domain is everything except what I remove. So all of this yellow is the domain of the function. Notice it is split into two distinct pieces. Okay, so what I have to do is when I write this in interval notation, I have to write two separate pieces and stick them together. Okay, and the way we do this, I'm going to do this piece first. Let me use a different color over here to try to illustrate a little more clearly what I'm talking about. No. Let's see if I can get it. Stand by. Man. I know what I can do. I can just draw over it. Yeah, perfect. Okay. Perfect. So I'm going to do this section first. So this section is from -infinity, comma. The upper boundary of this yellow section is the number 2. And I'm going to have an open parentheses because 2 is not included. This section in blue begins at 2 but does not include it and extends all the way to positive infinity. Now, because these two separate pieces are part of the same answer, I'm going to denote that they are stuck together using this symbol. This means union. Okay? It means the union of two sets, which is exactly what we've got here.
Can we do that in stats?
You did do this in stats, absolutely. So the union symbol in probability just means or, just like we learned in stats. So it means the values of x that are acceptable for inputting into our function are any x from this or this. Okay? So again, we have to break it up into two mini intervals. And then we have to join them together to indicate that collectively these are the set of possible x values for the function. Okay? You can eventually, once you understand this convention, you should be able to jump directly from this right here. Once you figure out this excluded value, you would just know that we would take the interval from -infinity to infinity, and this part is me cutting out the 2. So we'll see several of these. Questions so far? So if you have a question that has a rational function, aka a fraction with an x or a variable in the denominator, you will need to figure out where that denominator will equal 0 and remove those values from your domain. Okay. So you'll have to be like, fraction, bad, denominator can't be 0. Then you'll go ahead and set about your work of excluding the values where that happens. Okay, so there's multiple steps to kind of getting through that. All right, now let's talk about, and I'll go back and reformat this. Some of my stuff is out of order. So here's your how-to for that. Step by step, this is what we did. Identify the inputs, identify restrictions. If there is a denominator in the formula, set the denominator equal to 0 and solve for x, blah, 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 blah. There is exactly what we just did, and I'll get rid of some of this space. All right, so now let's talk about given a function written in equation form, including an even root, and this is very specific, like a square root, or a root, or a fourth root, or a sixth root, or an eighth root. You're going to follow very much the same idea, except there's going to be a different set of numbers that are going to cause a problem. So find the domain. Find the domain of the function f of x equals the square root of 7 minus x. Okay. So I do have an even root here, and recall that if there is no index in the root, there's an understood 2 here. This number is called the index of the root. It tells what root I'm taking. This is a square root. It's so common that we just drop that 2, right? But this can be any number. And if it is an even number, then what I'm about to do applies, okay? So what we need to understand here is if you look at 2, it says since there is an even root, we have to exclude any numbers that result in a negative number in the radicand. And that is just a vocab word. The radicand is what is under the root. This cannot be negative, right? So it cannot be strictly less than 0.
that make sense? Right. So
We want all of the values set equal to 0, and we're going to solve. So I'm just going to take this guy, and let's look and see where that's going to work. So this will be, they're doing it greater than or equal to 0. So this would be 7 minus x greater than or equal to 0. And these are the values that I'm going to keep. Okay? Because those numbers under that must be positive. So let's just solve using the normal solution methods. Miracles of algebra. We're going to subtract 7 from both sides. We're going to divide by a negative, which ultimately flips the inequality. So x must be less than or equal to 7 in order for us to keep that. So again, remember your default domain is going to be everything. So just to draw you a number line, let's say this is 7, this is 8, this is 9.
Can we have 0?
What is it?
Can we have 0 underneath?
You can have 0, yes. Because 0 is non-negative. Does that make sense? So we can take the square root of 0 without an issue. So yes, good question. All right, so x, and looking at the number line, x is less than or equal to 7. So this would be closed. And then we would include everything here. So the domain of this function, let's write this interval, would be from negative infinity up to and including 7. That's an inclusive endpoint. So we want to make sure to use the bracket, bless you, and not the parentheses. So sometimes it's a little difficult to think about this. So just while you're reasoning through it, let's see if I take a number from this and plug it in here, if it works. And then we'll take one that isn't in this and see if it works. This is me checking my work. Okay, this is me just making sure that you understand exactly why this is so. So a number that is from negative infinity to 7. Let's check our work. So let's check x equals 6. So f of 6 is going to be the square root of 7 minus 6, which is the square root of 1, which is totally fine, right? Is that cool to do? Fantastic. That one works. So now let's check one that is not in our domain. Let's do f of 8, because that's definitely not in this interval, correct? Okay, so let's see what happens. 7 minus 8, that's going to give me the square root of negative 1. That doesn't work. That's not allowed in the real numbers, right? We can go into the imaginary numbers, but when we're working these problems, we are under the assumption that we have to stay in the real number system, no imaginaries or anything like that, okay? So this is the second weird thing that you're going to consistently have to account for. You're looking for variables in the denominator for which the denominator cannot be 0, and you're looking for radicals of even index, square roots, fourth roots. And in that case, you must check to ensure that what is under the radical is not negative. Okay? It cannot be negative, and you have to find that range of values. Question so far? Okay. All right. We're making great time. All right, so now let's talk about the different types of notation. So the only real new one I'm going to introduce to you is this one. It's called the set builder notation. And so it's going to be it's basically a language thing, right? It's just understanding how to read these symbols. And I will make sure that that's up there in words at some point. So if we're looking at this first example, here it is on the number line. We do not include the 5. It's got an open circle, right? This is an open endpoint, which means that we're going to use, in the interval notation, we will use the parentheses. 10 is a closed circle. It is included. We will use the bracket. Inequality notation is pretty straightforward. H is between 5 and 10, not including 5, but including 10. Does that make sense? The set builder notation uses inequality notation, but adds another component. These curly brackets indicate a set of numbers or a list. And this means all H such that
this criteria is met. So this is read, all values of H such that H is between 5 and 10, not including 5 and including 10. So you see how it's directly taken from this, and you just have this new piece here that just, we're trying to confuse you on purpose like this. This is a very simplistic example. It doesn't seem like at this stage that you're like, why are we even doing this? As we progress, this will become useful. At this point, it's kind of redundant, but just to illustrate that this is not a scary thing. It just means all values of H, the input, such that this criteria is met is what we include in this, right? So, and these are just other examples, right? With the strictly less than or one endpoint and infinity is the other endpoint. And so this is all a really natural progression from that. You will recognize this one down here. You will if you've had a class with me. You'll recognize the set builder notation that you're very likely familiar with for the set of real numbers, which is the double bar R, the bolded R. And so this is perfectly valid for the set builder notation. But I will explain to you if I say express the domain in set builder notation. This is set builder notation. This is interval notation. They are different. Does that make sense? You have other letters that denote sets of numbers. You have, C for complex numbers, blah, 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 blah. We won't really talk a whole lot about those, but that double barred R, you need to know what it means. And I'll show you how it looks when I write it, because that's kind of small. This is double barred R, real numbers. My pre-cal people will recognize that. You're welcome. All right. So all that being said, this is really more of a reference for you just to kind of introduce you to it. Let's do an example. So let's write this one in all three notations. Let's write this. If you want to sketch this down in your notes, that's fine. Let's write this interval first in inequality notation, because this is something I'll ask you to do. Example. In inequality notation, notice I have two endpoints here. So I'm going to say, okay, 1 less than or equal to x less than or equal to 3. And so this comes from, I know x's are between 1 and 3, and the equal to part comes from the fact that we include those endpoints. And then this section is simply, x is greater than 5. So I have these two pieces, and we join those together with the word or. The only time we use the union symbol is in the interval notation. So again, x is between 1 and 3, including 1 and 3, and x is strictly greater than 5, aka not including 5. All right, now let's do the set builder. Bless you. Set builder includes curly braces because it is a set, and includes all x such that this, the inequality just goes there. And then finally, let's do the interval notation. This would be inclusive 1 to 3 inclusive, union, because I have 2, open 5 to positive infinity. Questions so far? Feeling okay? Kind of, sort of? Right. Good? Everything good? All right. Can I scroll? We're good? All right. Now let's talk about domain and range from a graph. Okay, so visually this is like challenging for some reason when you first start picking this apart. Oh, it's cool. It's all right.
It's not that serious. All right, so if I give you the function in blue, when I ask you to look at the domain for this function, what you're actually doing is looking only at the horizontal part of the graph, right? Like we need to pick this apart in terms of what is happening horizontally and what is happening vertically for the range. So that being said, let's define some things. The domain is all possible inputs, and we find this on the horizontal axis. Basically everywhere the graph touches horizontally, right? But you're only looking, see how I've reduced it to a number line? And the range, if you recall, is all possible outputs. And this is found on the vertical axis. So you kind of need to pick that apart in your brain. So let's look at the domain. And remember, we always move from smallest to largest when we're working with interval notation. So that means we are writing this from left to right and from bottom to top. Okay. All right, so let's write the domain. Domain for this function. Moving from the left, the first instance of the graph I see occurs, and I'm only looking at this one, at -5. Is -5 included? Yes, it has a closed circle, comma. And then I just need to figure out, where does this graph stop? So because this graph has this arrow here, and it is slowly but consistently moving this way, that will be extending indefinitely or to infinity in the positive direction. So this function's domain is all the way to positive infinity. If there is an asymptote, there'll be a way for you to know that, okay? An asymptote is an imaginary line where the graph approaches but does not cross. Yes?
Why wouldn't it be negative?
Why wouldn't what be negative? Ah, that's an excellent question. I'm so glad you asked. We are only looking at the horizontal component. The graph does go down vertically, but horizontally it is extending to the right, and to the right is positive. Okay, so it's a matter of training your mind to only look at the horizontal component and completely ignore the vertical. And it takes a little bit of practice to pick those things apart. All right, so the domain for this function, -5 to infinity. Now let's look at the range of this function. So starting at the bottom, this graph will continue indefinitely to negative infinity. So that's where it will start the range. It goes from negative infinity, and it goes up, 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 up. And what is the vertical value at which it stops?
5.
5. So that's going to be this. Do we include it or no?
Yeah.
We do. So that's going to be a bracket. There you go. So it takes a little bit of practice. All right. Let's do another one. Let's do an example. All right, so looking at the domain of this function, example, the domain. And sometimes I like to use color like this, like the domain it goes from X here to X here, right? It's bounded between those two X values, okay? And so I'm gonna write that as we begin at -3, parentheses, because it is an open circle, and we go across this number line to 1, and we will include 1 because of the closed circle, okay? And then the range of this function, this is its lowest point, and this is its highest point. So anything in between those two is what I'm looking for, okay? But it's only on this axis. So the range of this function, remember we start at the bottom, its lowest vertical value is -4 and moves all the way up to 0. Okay? You might be tempted to put -3, but that is a horizontal axis value. When we are talking about the range, we do not consider that at all. Yes?
So what if the dot that's on -3, 0 0, what if it was dropped down to like negative, -3,
If it was dropped down, if there was an open circle, okay, that's a good question. So if there was an open circle here,
Yeah,
Okay.
would you count that, or would you count the highest point? And if you did count the highest point, would it be open or closed? Or, you see what I mean?
Would I need to exclude this value, is that what you're asking?
No, I guess the curve
Actually, I'm gonna
goes,
edit that 0, now that I'm looking at it closer.
the curve goes up. So when you're looking at the range, the where it intersects on 0, 0,
Yeah, I need to put a close bracket.
it'd be closed.
It would be close.
Okay.
So do y'all hear his question?
No.
he caught me slipping. Good job.
Let me try.
Slipping. Look, tell me, see if you can notice why I did this.
Because the function still goes into the 0.
Yes, it's still touching. That's closed circle. Closed circles supersede open circles. Thank you for asking that question. I was so focused on doing it with everything else I was doing, I missed it. All right. Now, if there was an open circle here, would I exclude -3 from the range?
Yes.
No.
Well, no, because some of the functions still
Right,
exist.
because it happens here. So because the function exists here, it doesn't matter that it doesn't. Right, this number is excluded in this function. Does that make sense? Now, let's talk about another example.
So we would still include everything from
Yes.
-4 all the way to 0.
Now, what about this?
Well, we need to exclude it.
Now I would exclude the -3 because there is nowhere in the curve where a value occurs at -3. There's a distinct cut through the entire function. Right? Would I exclude -3 now?
Nope.
No, I would keep it. Let's see, would I exclude 0 now? Yes, now I would exclude 0. Would I exclude -4 now? No, because of this closed circle. Okay, let's look at that.
You just have like 3 separate or 4 separate functions.
No, you would actually only have 2 pieces. So let's,
If you had all the negative terms excluded,
yeah, because if I'm talking about the range. Let's do it again.
Okay, I see, I see.
Okay, let's do it like this. Let's do the range and the domain like this. That's not a really nice value. So let's just do the range. So basically what's happening is there's a cut in the graph right here. So in this instance, the range would look like this. It would be -4 up to -3, and then it would pick up again at -3, and it would go all the way to 0. So notice all I've done here is this range is exactly this one. Its endpoints are still the same. But now this has been cut out. I've just cut out the middle where those places will be. Yes,
And it doesn't affect the domains.
it would affect the domain.
So
But like, we're gonna have to make an estimate because these are not nice values.
And you would cut all those out?
Yeah, there's going to be like 4 pieces of the domain now. Let's just do it. We'll estimate with a decimal. This is the range. We'll say domain. All right, so domain, the cool thing is if you look at the endpoints of the domain, they're not going to change. We're just going to do some stuff in between these. So we'll have a cut at about what, -2.5? Do you agree?
Oh, that's -3.
And then union, it's going to be -2.5 again. So from -2.5 moving over, the next break is at approximately -1.3. Open, union again. And now I'm doing this section. So it starts up at -1.3. Fix that.
You're doing great.
I'm working on it, girl. Let me see. I'm on the fly here. I love this. All right, so -1.3, which is about right here. So now let's do this section. It's going to go to about, what, 0.9? Golly, this is a lot. All right, so that's going to be open again. And I've still got one little section left, right? One teeny tiny section to the right of that last open circle. So it'll be, I can't get it to scroll over because they haven't come and give me a projector screen yet.
There you go.
There, I got it. All right. So now union one more time for this little teeny piece right here over to the side. That'll be 0.9, and here is the endpoint that I was expecting to see. But again, notice that this endpoint is here, and I left the negative off. And then this endpoint is still here. And I've just got a lot of breaks going in between. Good? Is that better? Okay, cool. Yeah, that escalated quickly. I love questions like that, though. So this is just a visual of exactly what we just did. The domain goes from here to here, range goes from here to here. Look, they did the same thing. Bad textbook. There. Fixed it. All right. All right. This is another kind of reference kind of thing for you. I don't expect you to write all these down. Do you remember me yesterday or the day before talking about, hey, you've got to know these toolkit functions for when we do domain and range? Here they are again. And I'm going to go through with you and talk about the domain and range of each of these toolkit functions. And it will do you so much good because domain and range is so much easier with a visual graph. Okay? So if I give you an equation that uses one of these toolkit functions, you can use your knowledge of the toolkit to build the domain and range, even though I don't give you a picture. Because most of the time I'm not going to. You have to construct the picture yourself without the use of technology. Okay? Just by reasoning through what you know. So the constant function, the domain is all real numbers because it goes indefinitely horizontally, right? So it's negative infinity to infinity. Can y'all see this or you need to say it more? Good. The range, the vertical component of the graph, it's only one number, whatever C is. So if this is X or Y equals 2, this would be close bracket 2, comma 2, close bracket. This 2 is the only thing that exists on the vertical axis. Make sense? Yep.
Is there any, when listing the range, where you have to do two?
Yes.
Like,
The
there's
convention-
not one.
No, the convention is just like this. The endpoints are right there. Now that's just, now could you just write, like mathematically speaking, would it be okay for you to do this? I mean, I guess, but that means something different, so we're not going to do that. That means something that y'all will probably not learn unless you get a full 4-year degree in mathematics, so don't worry about that. Anyway, so the identity function, remember when we're talking about domain, we not only have to conceptualize it in terms of the graph, but we have to remember what the domain is. The domain is any X values that have a restriction mathematically. Remember, we've only learned about 2 times that happens. That's negative even roots, a negative under an even root, or an X in the denominator where it can be undefined. Notice a linear function of any kind, which that's what this is. It's a base linear function. It has no restrictions. We can plug in any number to a linear function and get another real number out. Like there ain't gonna be no undefineds in a line. Right? So the domain is defaulting to all reals. The range also defaults to all reals. So if you have a linear function, you can automatically go here. There are no restrictions on linear functions for domain or range unless specifically indicated. Does that make sense? Kind of, sort of? Cool. All right. The absolute value function. Hey, in pre-cal last year, if you were with me for pre-cal, we actually talked about this function in detail. And we expressed it as a piecewise function, which we'll do a little bit later. For absolute value, there's no restriction on what we can put in for X because all it does is take it and returns the positive version, right? I can put in negative numbers, I can put in positive numbers, it's fine. So notice the horizontal component of the graph, it starts at negative infinity and just continues to negative infinity forever, or positive infinity forever. The range, however, remember the range is the set of outputs for the function. So no matter what I plug in, am I ever going to get a negative number out of an absolute value function? No. So the range is only from 0 and up. It does not, we have taken out all of the negative numbers because there's no possibility of a negative number coming out of this function. So you have to reason your way through, what does the absolute value function do? Well, it takes everything and makes it positive. So the outputs for that function will be everything except the positive numbers. So would we include zeros?
Yes.
Yes, the absolute value of zero is zero. Then it starts to flip-flop. The absolute value of -1 is positive. So that's why it only exists vertically in the positive quadrants. All right, quadratic functions. You can plug any number in and square it. Because remember, that's what a quadratic does. It squares a number. Is there any number that I can't square? No, so the domain is every number, always, negative infinity to infinity. However, the range, the outputs of a quadratic function, can I square a number and get a negative number? No. Therefore, the range is all non-negative numbers, 0 and 1. And you can see that expressed visually here because we're only in those positive quadrants. Okay? The cubic. Is there any number I can't multiply by itself 3 times? No, that's all a cubic is. 2 to the third power is just 2 times 2 times 2. I can do that for any number. And you can also visually inspect the parent graph here, the whole kit graph, and see that even though it's moving slowly forever in that direction, it will go that way to negative infinity forever and this way to positive infinity forever. Will it, does it go down forever? Yeah. Up forever? So the range of this function is everything. Just think about it. If you plug in a -1 to this, what do you get out? -1. It doesn't do odd powers don't change signs. So it doesn't restrict stuff to being up here. You plug in a negative, you get out a negative. Plug in a positive, you get out a positive. So everything is included in this factor. All right. Also any odd power. Any odd power will do that. Right? This is the reciprocal. So this is our first instance where we have one of those cases where we have to restrict specific numbers in the domain. We cannot plug in anything that is going to give us a 0 in the denominator because that is undefined. So we have to take all those numbers out. We have to figure out what they are. So the only way 1 over x is undefined is when x equals 0. So that's going to put that 0 in the denominator. So notice, in my domain, I have the standard negative infinity to infinity, but I've removed the 0. I've taken 0 out. Notice how it does not cross over x equals 0, which is this line. Makes sense? Same thing for the range. The range is a little trickier. You can conceptually understand the range for the reciprocal function by understanding that there is no instance ever that I'm going to plug anything in here to make this 0. Because there's just no way it can happen. There's a 1 on top. You can plug in anything you want to. This is never going to be 0. The only way you might even try it is putting a 0 down here, but we already said we can't do that. Yes.
So with that, do they eventually like cross over each other if they go vertical?
Not this one. There's a horizontal asymptote at 0 and a vertical asymptote at 0. Like they will start doing funny things as the reciprocal function gets more complex. But for our purposes, we're just working with really basic stuff. Okay? And if it did become more complex, you would need to inspect the graph. But that's why I teach you to connect this to this. Because you can like put a graph up here and be like, oh, okay, I kind of see what's happening. We will not do a whole lot with this one, but the idea is the same, right? So if I have a fraction, this is the reciprocal squared, 1 over x squared. Remember, your 2 deal breakers for domain are division by 0 and negatives under even roots. There's no root here, so it's not that one, right? But I can get a 0 in the denominator by undefined by plugging in 0 to the denominator, so I have to restrict 0. Now, why does the range only return positive numbers? Because of the square. Anything you plug in is going to immediately become positive because it squares it. So that's why that flips on top of that.
Square root is really important because this is one of those weird ones that we have to look out for, just like something in the denominator. This is the other one. Can't have a negative number under the square root, under the right. So notice the domain, the only numbers that I can plug into this function without getting a negative number under here are clearly, numbers that are positive or zero. Therefore, because nothing can come out of this that's negative, the only possible outputs for the function are also positive. Because if I can't plug in a negative, certainly a negative is not coming out. This one is really important to connect visually because I'll ask you, I'll add some craziness under here, and you'll have to figure out what it's doing. But we'll work with that. I'm not worried about the cube root. Pretty much, the cube root is like the cubic. It's got everything. There are no restrictions. It's only even roots, and I will try to trip you up with that. Like if you see an odd index, 3s, 5s, 7s, 9s, 11s, 547s, it's going to be all reals. Because odd roots don't change anything. They don't change a sign, or they don't have any restrictions on what we can put in there because it's not going to mess anything up. All right, I know that was a lot, but it's worth it. Given the formula for a function, determine the domain and the range. This is what usually students struggle with. The domain is usually not as big of a problem, but the range is. The range confuses people, and it comes from you not memorizing those toolkit functions and knowing how they move around. Do you remember transformations of functions? Shifts up, shifts down, shifts left, shifts right. We're going to put that to use. Okay? We're going to put that to use when we find the range. All right, let me find my example that I want to use. All right. Find example. Find the domain and range of the function f of x equals, I'm getting old, y'all, 2x cubed minus x. All right, so notice I've got a list of how-to steps here if you kind of forget where you're going. Exclude from the domain any input values that result in division by zero. Do we have any possibility of division by zero? No. Exclude from the domain any input values that have undefined number outputs or non-real, and that means the negative in the square roots. Is there a root anywhere?
No.
No, so there are no restrictions on the domain. So the default domain for any function is what we're going to go with because I'm not taking anything out. And if there are no restrictions on the domain, not going to be any on the range either. Because essentially what's happened here, I mean, it's just kind of some crazy looking, there's only two times where something's going to mess it up, and that's the negatives under the even roots and the division by zero. Look at the function graph and the table values to confirm. What tool on your Chromebook might you use to go graph this and take a look at it? Desmos, right? Let's go again. And put some space in. And I will encourage you to, as you're working through your problem set, to check your work using Desmos. Just to get a visual, especially when it's a super weird function that you can't visualize on your own like this one. All right, let's do find the domain and range. Of the function f of x equals 2 divided by x plus 1. All right, so are there any even roots? Nope. Is there a possibility of there being zero in the denominator? Yes, there is. So we have to restrict the domain. Okay. So where the question is going to be denominator equals zero, exactly where? Well, at -1. So we have to remove this. We have to remove this. Okay, so the domain, remember we start with a domain of everything, but we're just going to take out that -1. So we begin at -infinity. We're going to go to -1, take it out, and then move to positive infinity. And if you would like to employ the number line, please do so.
Why is it that when we write infinities, we use parentheses and not
Is it-
Because you can never like that's an endpoint, right? Can you ever get to the end and include infinity? No, and that's why. Conceptually, that is why. So again, we are excluding this number, and our domain is going to be all of this. So we take this piece and put it here, join it together, or take the union with this upper piece. Okay? All right, so now we have a problem, range. This one is conceptually a little more tricky to think about, and you're going to have to like make your brain do it, okay? Like you're going to have to understand that there is no way, because this is a number, there is no way this function will ever equal zero, no matter what I plug in here. Doesn't matter what I plug in here. This thing is not going to be zero. You're welcome to investigate it if you wish. Because essentially, when you're looking at a function like this, the output of the function, you're basically looking at this. Like, is this ever going to be zero? Like 2 divided by what gives you 0? 2 divided by 0 is like 5. Is there anything I can divide down here that will make this 0? No. So you need to understand, if there is a number in the numerator of a rational function, aka a fraction, it's never going to be 0. So 0 must be excluded here. So never equal to 0. So we have to exclude that. And that's a trick. So let's exclude from the range the value 0. This one is more conceptual. You have to just understand that and remember that that number on top can't be 0. See, if it were me, I would sit there and plug in a whole bunch of numbers and try to make that happen because I'm a skeptic. All right, questions so far? Okay. All right, let's do another one. Let's do another one, and you can probably guess what type of restriction I'm going to show up here. So find the domain and range of the following function, f of x. What?
A question was asked where 0 can't be in the range.
Because this, remember, the function outputs are the range. So this right here, there's no way this plugging anything in here is ever going to give you 0, because there is no number that exists that you can divide into 2 that gets you 0.
Because a fraction is like a piece of a whole, and you can't have a whole lot of zeros.
Right.
It's not.
Exactly. You can't have like, no, that doesn't work. You can't divide something into 0 pieces. That's like magic. We can't do that. We don't know what that means. So f of x is equal to 2 times the square root of x plus 4. So remember, we're only on the lookout for 2 things. X in the bottom of a fraction. Is that happening here? Or an x under an even root. That's definitely happening. So from the domain, we have to exclude any negative numbers. So to find the domain, I'm looking for only x values that are greater than or equal to 0. Why don't I include the root here? Because I don't care about the root. All I'm doing is looking for where what is under the root is negative or positive. So there's no reason to do anything to it. Even if you did include it, you'd square both sides and 0 squared is 0. So it doesn't matter. But I'm only looking for this. Right? So, miracles of algebra. Oh, look, that's so easy. Okay, so this domain is going to look like this. It's going to be -4. So it's going to be everything at -4 and up. And so the domain of this function includes -4 and extends to positive infinity. Why don't I care about this?
It doesn't affect what's on
Right, it doesn't, the only thing I'm interested in here is this being negative. So it doesn't matter if whatever it is multiplied by 2 later, I don't care. It's literally irrelevant to what I can plug in here, is this piece is the only thing affecting there being a negative number underneath this.
Why isn't the line, like the on the number line, facing the other way? Oh wait, never mind. I'm going to go. Actually,
Yeah. Because we just don't write it like that. It's always less to greatest. Remember, as we move from 0, negative gets larger in magnitude this way. Yeah.
I just wasn't.
No, it's a good question. There aren't any really dumb questions. I mean, it takes a little bit of practice for some reason to get used to writing negative numbers on the number line. I have to think about it. It's difficult. All right. So let's do the range now. Okay, so the range is difficult to think about. I'm like, all right, so basically the question I'm asking myself is if I take this domain, if I only plug in numbers, -4 or bigger, what are the possibilities for what's going to come out of that function?
0. Positive. 0.
They're definitely going to be positive, but which ones? I'm not saying you're wrong. You say 0? Not everything, because no negatives are coming out of here, right? Just positive. So let me show you how much easier this is to do with the graph. So let's transform this. So I'm going to draw a junky sketch. If you were in my class last fall, you know what that means. Just a junky, like crappy version of whatever I need to see. So if you recall, the toolkit function for the positive root starts here. So what has happened vertically as far as a transformation of this function? Why do I only care about vertically?
Because we're on range.
Because we're on range, and that's all that matters. I don't care what it's doing side to side. All I care about is up and down, because I'm talking about the range. Are there any vertical shifts?
Yes.
There's a stretch, but not a shift. So watch what happens when I stretch it. It just goes up there. It doesn't change that starting point. Okay. It is going to shift it to the left 4 units. Does that do anything vertically to the graph? No, so I don't care. So the range here is just 0 and up. Inclusive 0 and up. Now you can confirm that, because the worst case scenario, the lowest number you're going to have is that -4 going in algebraically. So if we plug in a -4 here, I get the square root of 0, which is 0, times 2, which is 0. So that's my starting output value. For me, this is much easier. You can do whichever one you want. But I like to, especially with the square root function, I like to use the vertical transformations. And again, for the range, I don't care about anything except for any shifts that are going to go up and down, or a reflection. If it were to reflect, if this 2 was negative, this would go down here, and the range would be reversed. It would be negative infinity up to 0. That's where your function transformations come in handy, right? Because you know that a negative multiplied out front of the function is going to flip it over the horizontal axis. And that definitely messes with your range. Right? So we're taking everything we've learned in algebra 1 and 2 and we're applying it to do new things. Okay? All right. What else have I got here? Oh, the piecewise functions. Ugh, gross. Gross. All right, piecewise functions. You probably remember these. Maybe you like them, maybe you don't. Basically, all this is it's a function. It's a single function with multiple rules for each section of the domain. Okay, so for certain x values, we do one thing. For other x values, we do another thing. For other x values, we do another thing. There are a different set of instructions for each component of the domain. So the way we write this is f of x equals this giant bracket, which says to us all of these rules are part of this function. And then it says use formula 1, it'll be listed there. If x is in domain number 1, use the formula number 2 if x is in domain number 2. So if we're looking here, this is the absolute value function written as a piecewise function. We tell people, hopefully this is the way you done. We did this one. So what the absolute value function does is, here's formula number 1. If x is greater than or equal to 0, and you negate it or do the opposite if x is less than 0. So let's use an example. So like for if x is let's say if x equals -5, aka tell me f of -5 for this function. Well, -5 is the input. So I'm going to go here and look at where this input of -5 falls to figure out which rules to apply. Okay. So I go here first. So -5, is it in domain number 1 or domain number 2? So x is greater than or equal to 0. -5 is greater than 0?
Oh, it's that, I thought.
It's okay. So -5 is less than 0, so I use this one. So let's see what happens. So I apply the formula negative x, so that's negative whatever. So the -5 goes in. What comes out? +5. Is that not what the absolute value function does? It takes a negative and turns it positive. Check. All right, let's do another one. Let's say find f of 2. So that's this candidate right here. That's domain number 1, right? It's greater than 0. Well, in that case, I apply this formula. Well, it's just simply the same thing. So that just means we don't do anything to it. Does that make sense? Complicated way to say something very simple. All right, let's talk about this. All right, so we're going to do a piecewise function with the following. So this is sketching piecewise functions. So if we have f of x equal to x squared if the domain is x less than or equal to 1. It's just 3 if x is between 1 and 2. And it's simply x if x is greater than 2. So the first thing I want you to understand here is if you notice these 3 domains, there are no overlaps. There's no overlap in here, because if we did, we'd be violating the definition of function. So there are never going to be overlaps when you're working with these. It's just going to be pieces of the domain. All right, so x squared in general, and I'm going to ask you to graph these, and you need to know the toolkit functions in order to do so, okay? You got to know kind of what those look like. So I've already got the quadratic graph down here. In order to graph this quadratic, I'm going to know that the vertex is at 0, 0. I'm going to know that there's one anchor point at -1, 1, and another at 1, 1, and then I'm going to sketch that graph. So that's what it would look like, right? But notice it says this function only exists at x less than or equal to 1. And so I'm going to cut that graph off everywhere else. There's the domain for x squared. X less than or equal to 1. Do you see it? Okay, so for the next bit of the domain, x between 1 and 2. That's this. So now let's graph the function 3. This is a constant function. If you remember from your toolkit functions, it looks like this. It's just a horizontal line at 3. But it only exists in this blue piece of the domain. So I'm only going to graph it in between that. So instead of that whole line, I'm going to just graph that from here to here. Let's see. X equals 3. Nope, still wrong. What's wrong with what I did just now? Yep, closed circle is on the left. Okay, that one's good. And now simply x. This is the identity function, f of x equals x. It's a linear function, slope 1, positive. So I'm going to draw that just so you can see it. Remember, that function does this. It goes from here to here to here to here and continues. That's the identity line. That's this one. But where does it exist? Only greater than 2. So only in this section. So where am I going to graph that line? Just in that section. So I'm going to get rid of all of this. Do I include this endpoint? Not for this one. X strictly greater than 2. So here's the graph of the function f. It has 3 pieces: quadratic, constant, and a linear. And what I've done is chop it into its respective domains. If you notice, looking at this graph, moving from left to right, do any of these graphs overlap and occupy the same horizontal space? Because as we move here, where there's a closed circle here, this constant graph doesn't exist. There's no overlap. There's no violation of the function. In other words, for the input 1, there's only one output. And then as we continue across, where there is a closed circle for the constant function, there is an open circle for the linear function. In other words, for the input 2, there's one and only output for this collective function that has been cut into different pieces for different pieces of the domain. So we call it a piecewise defined function. Because we define pieces. So here you're going to draw on your knowledge of functions. You're going to draw on your knowledge of graphing basic functions that we learned previously. Now we're also going to apply the idea of domain. So this really ties everything in together that you can talk about. Real quick, a question that I wasn't going to ask, but I will. What's the range of this function?
0 to negative positive infinity.
Yeah, 0 to positive infinity. So let's do that. Let's do the range. It goes from inclusive 0 to positive infinity vertically. And let's just go ahead and define the collective domain and interval notation. We start with negative infinity to infinity. Are there any breaks? Is there a break at 1? Yeah, it's included, so there's not a break here. Is there a break at 2? No. Uninterrupted everything. Yes.
What was the input to get 0 in this function?
What was the input to get 0?
Yeah.
X is less than 1. Because if x is 0, that qualifies under this domain. 0 squared is 0. That makes sense? Okay. So to determine which formula you apply for a particular x, you need to find which domain it falls in and use the associated formula. So you almost work it backwards this way. Okay? And I think that's it for today. Long lecture today. I'm going to give you your problem set. And give me a second and I'll decide exactly what I want you to work on. All right.